Hello, my name is Ioannis Farmakis, and I'm PhD candidate at Queen's University. Today, I'm presenting on the Rockfall detection using LiDAR and Deep Learning. The outline of my presentation starts with the motivation and a little bit of introduction to the methods and materials used before we formulate our Rockfall detection problem and provide a brief introduction to deep learning. Then I'm going to introduce the datasets used for the development of the models and the neural network architectures that test. Finally, I'm going to present the results and conclusions. Today, in engineering geology, we have the ability to build digital replicas of our rock slopes and leverage 3D visualizations, check precise measurements, and change detection tasks. However, there is still a long way for an intelligent model to make our models more intelligent and actually leverage autonomy, which is the focus and the goal of this research. The motivation of this study is that Rockfall risk management is based on today on statistical analysis of historic frequency magnitude patterns for an estimation of the return period of given magnitude ranges, meaning that we have a magnitude and a temporal component. Today, with LiDAR and the advances related software, we have the ability to do spatially accurate rockfall monitoring. And this wealth of digital data supports the research to develop AI approaches to identify, analyze, and most importantly, predict spatio-temporal rockfall patterns in even real time. However, prerequisite to the development of an autonomous system like that, that is able to map these spatio-temporal rockfall patterns, is a rockfall detection algorithm that we wanted to identify rockfall events as they occur, to update the predictions on time while we constantly monitoring the sites with automated LiDAR systems. There's something similar to the object detections that we have in automotive, with a goal to identify other vehicles, traffic signs, traffic lights, pedestrian trees, etc. However, there are important differences between these two applications. A car, for example, as we see in the video, a car is always a car at every point of time, can be identified within static data, which is the frames of the video, a sequence of images, and non-volumetric data are sufficient for this task. In this video, in every second of this video, the car is still a car. However, a rockfall, which is defined as a discrete rock fragment detached from the face of slope and propagated downslope by falling, bouncing, and rolling, it's not a rockfall until it is detached. It requires, for example, in the beginning of this short video, this part that failed was just another part of the slope that after some time it became a rockfall. In order to do that, we need multi-temporal data to identify that this specific volume finally becomes a rockfall, and also volumetric data are required to do this detection, 2.5D or 3D, preferably 3D. As such, with LiDAR-based rock slope modeling, we have this volumetric point cloud data to do the analysis. We identify volumetric changes through change detection algorithms, where loss areas represent the detached material. And then we do the spatial clustering of the loss volumes to create individual point clouds, but not all changes represent rockfall events. Since we have our different point clouds, the rockfall detection problem becomes actually a point cloud classification problem, which is the task of assigning a class label to a particular point cloud dataset that is different to the semantic segmentation, which denotes the per point class assignment within a given point cloud dataset and usually generates a confusion between the two concepts. The point cloud classification problem is similar to the well-known image classification problem when we have an image that we want to assign a label to the image to describe the context of an image. This image classification problem, it's pretty much a solved problem since the release of convolutional neural networks in deep learning. But to apply convolution operations directly on point clouds, it's not a trivial task. However, there are also methods to apply deep learning to point clouds. And in general, what deep learning does is that it involves algorithms, the artificial neural networks that are used to create the algorithms for a task that's too complex for a human to develop. Meaning that if we have a problem that we need an algorithm to solve it, and this algorithm is too complex for us to develop it, with deep learning, you use the neural network that, based on the experience that we provided with in the form of data, it learns what is the appropriate algorithm to solve this task. So the most crucial component of deep learning is the data. Deep learning is the process of learning from data using brain simulations, and is known as artificial intelligence. Deep learning algorithms seeks to exploit the unknown structure in the input data distribution in order to discover good representations that often happens at multiple levels. As such, deep learning gets us closer and closer to the raw data without the need of human involvement. For the development of the models that we tested for this specific rockfall detection application, we used two datasets. The first dataset is a 5-year-long LiDAR-based change detection database with a total of almost 9,000 information clusters. 38.7% of those represent rockfall events. All the clusters in the database are manually labeled as rockfall and non-rockfall instances. If a cluster was detached from an outcrop area, it was labeled as rockfall, and the situations of non-rockfall events include zones of talus and scree accumulations that subsequently move and appear as signatures of loss. Upper areas, for example, of soil, as well as the movement of non-indigenous individual rock blocks. And all of them, all of this process was also supported by optical material gigapixel resolution to identify and inspect what are the source zones that correspond to these changes. So we have the whole database of the different monitoring campaigns from 2013 to 2018 with different intervals, the different number of deformation clusters and percentage of rockfalls. We split it, all of them, in 3 datasets: the training dataset, the development dataset, and the test dataset. The test dataset was used to evaluate the model performance on a real-world example of the monitoring program, meaning that for this region, we selected the data detected in the last 2 campaigns, aiming at simulating a situation where what would have happened if we had this model already by the time. And the rest of the data were divided for each class into 70% for training and 30% for development, based on the volume distribution. This was based on the observation that the larger the deformation volumes are, the more discrete the shapes become between rockfall and non-rockfall deformations, and thus the easier the labeling is for a human. As such, the above practice was carried out to make sure that both training and development sets that are crucial for the development of the model come from the same distribution, and no such bias is induced in the training process. The second dataset that used is a different slope from British Columbia again. The White Canyon West part, which represents a geologically and geomorphologically different environment than dataset 1. It includes discrete geomorphologic features like large debris-filled channels and vertical dikes traversing the slope. And also we observe changes of different shapes in dataset 1 due to the fact that these linear features, these elongated features like the debris channel, for example, they provide the available space for the clusters to form a different elongated shapes as the material propagates downslope. And this dataset was used for two reasons. The first reason was to examine the potential of generalized applications of a model that was developed based on a dataset or on a database coming from the dataset 1, on the clusters coming from the dataset 1, which totally failed in the application. And the second reason was to examine the suitability of the proposed deep learning architecture to be used for site-specific applications, meaning that what is the ability of this model to learn again something useful from another site. And for this task, we used actually three different models, the different approaches. The first one is the PointNet model, and the second is the PointNet++ with two different options, the single scale grouping and the multi-scale grouping down there. Going to the PointNet, to the initial PointNet application, the PointNet encodes the global shape characteristics of a cluster that we initially import into the model by calculating the CAD model through surface reconstruction methods, meshing, and then sampling a fixed number of points, because a neural network as a function requires a fixed number of input data. So from the raw point cloud, we generate the model, and without altering its shape, we sample uniformly from the triangulated surfaces, the points, the number of points that we want. And imported to the model, we calculate the global feature vector here. While the PointNet++, it encodes the local structure in the first applications with a single scale grouping on the bottom right figure, single scale grouping, and the other second application, the multi-scale grouping, which does a concatenation of the representation vectors coming from different scales of different areas of the shape. And the results were evaluated based on the training process, and the results were evaluated based on two metrics, the loss and accuracy. In general, there is an inversely proportional relationship between loss and accuracy. And in interpretation, the loss defines how well the model understands the problem and the confidence it has in the predictions that it's making, while the accuracy defines the real-world implications. We see here that the PointNet predictions on the test data set, they are in very good agreement with the reference data set. We see that the PointNet has a higher loss compared to the PointNet++ models, to both PointNet++ models, but the accuracy is higher. This means that although it is not so confident in the prediction that it's making, it's still making the correct prediction, the correct decision. And but it's not only the accuracy that matters; it matters also the quality of the errors that the model produces. It's very evident in the other side, in the other data set, where here we see again the results of PointNet and the reference data set, the manually labeled reference data set, and based on the data coming from the White Canyon West. And we see that PointNet and PointNet++ multi-scale grouping, they have almost the same accuracy and low loss. However, there is a difference in the quality of the errors. And here, while we still see the good agreement between the PointNet and the reference data set, when we go to the PointNet++ results, we see that we have errors that have occurred even in the very large volumes. And this is something that we also further evaluated with an error analysis that we did for both sides. We split the test dataset clusters into 4 volume bins, and we calculated the median loss within each of these bins. And what we observe from that is that there is a decreasing loss, meaning an increasing confidence in the PointNet predictions as the volumes increases, which verifies our assumption, our hypothesis on the human level performance and our experience on the human level performance on that. While we see, and this is very clearly demonstrated in the Milo 109 case, while on the White Canyon West case, we still see very low error and very low loss in all the classes for PointNet++, where we also expect it to be easier to do the discrete change shapes that this site forms. And we observe that the PointNet++ confidence is very low. The loss is very high for almost all the bins. And the most important is that the loss remains high even for high volume classes. In conclusion, LiDAR-based rock slope monitoring opens new prospects for further advancements in rockfall risk management using artificial intelligence. Rockfall detection comprises the cornerstone for the development of an AI-based early warning system, and LiDAR and deep learning can be the building blocks of it. To teach a model what is a rockfall, it must be provided with examples of both rockfall and non-rockfall events. The rockfall detection pointnet architecture was proven suitable for the task in both the examined sites, with accuracies fluctuating around and above 90%, pardon me. Rockfalls can be better separated from non-rockfall change clusters by learning their overall shape characteristics instead of focusing on the local texture. Since the rockfall detection volumes, since the non-rockfall volumes represent rockfalls that were once detached, they are composed of the same material, and as the texture does not provide any discriminating value. Instead, global shape encoding of rockfall clusters inherits signs of the failure mechanisms. This is also validated by the fact that pointnet errors are dominantly related to small volumes, while the pointnet++ models make incorrect decisions on large volume deformations too, which might lead to an underestimation of the hazard subsequently when it's integrated into an early warning system. Rockfall detection is not a straightforward classification problem, and the balance between accuracy and error volume distribution should be considered by engineering geology experts when training deep learning algorithms for rockfall detection. It is challenging to achieve generalization rockfall detection even with deep learning, even though the strength of deep learning in vision problems has been widely demonstrated in the literature. And finally, continued research on site-specific deep learning-based rockfall detection with pointnet and similar architectures is highly encouraged by the results of the current study. Here are the references that have been used for this presentation. I want to acknowledge all of the members, sponsors, and collaborators. Here is the contact information that you can find the latest of our research. Thank you very much for your attention, and I'm happy to take any questions. Thank you very much.